Hey guys, welcome back to week three. So in week three, Andrew really just mostly took his time to cover the basics of classification, that is logistic regression, as well as some extra stuff around basically problems around machine learning, such as overfitting, regularization, stuff like that. He also tried to cover some more complex um, gradient descent algorithms, but to be honest with you, the algorithms that were covered are not quite as advanced as what we need right now. So we won't worry too much about that. But if we start with, I've got down my notes here that, for these classification problems, we can try to apply what we've learned previously for linear regression, but it doesn't always work out. And I can illustrate why it doesn't always work out through the following example here. So this is trying to predict um, whether or not a tumor is malignant based on its size. And you can sort of see that, there's quite a clear divide, right? So
If you want to make
um,
prediction,
if you run this with linear regression, you might be able to get this line here, and you might be able to, um, try figure out, you know, that for tumors that are above a certain size, then they're certainly malignant, and you can sort of set a manual value. Say if a tumor is greater than or equal to 0.5, you can predict it's malignant, and it sort of works out. But if you then get another value to your training set, you can tell that the threshold should still be here. But the thing is, with this new data, if you run linear regression, suddenly your tumor size has shifted. And for a tumor to be malignant based off what you've previously classified, uh, it's going to be, you're going to have to set a new threshold. And this isn't a very robust process. For every new set of data or new data points, essentially your model sort of collapses in a way. There's also the issue that, this is quite a simple example. For more complex nonlinear examples, it can be a lot more difficult to set the threshold classifier. So to solve this problem, we essentially have to figure out a new way to, do this regression. And we do logistic regression, also known as classification. So the original function that we had that we're assuming to be our hypothesis function for the line for linear regression is going to be incorrect here, because we want to um, essentially model uh, the value theta tx as being between the ranges of 0 to 1. Well, ideally we want it to be either 0 or 1, but it's quite difficult to get that step function in there. So what we do for that is we use something called a logistic regression model, and we use the sigmoid function to model our values that we get from theta t, excuse me, theta tx, to try force them between 0 and 1, and that looks something like this: 1 over 1 plus e to the negative z, for the function of g brackets z. And if we combine these two, we get our new hypothesis function to be equal to 1 over 1 plus e to the negative theta tx. Something I should clarify from this function is that when you're training the logistic regression model, you really want to be pushing your z, which is your parameters basically times your x, out to one of these two extremes, either as close as possible to 0 or as close as possible to 1. Being in this middle ground is sort of, it's okay, like you can be there, but realistically, when you train it, you'll be pushing your values out to either end. And the next thing I've got down in my notes here is that the new hypothesis function for x is the estimated probability that y is equal to 1 on an input of x, and that's formalized down in this equation here, which essentially is saying This is the probability that y is equal to 1 given x with the following parameters theta. And if you, sorry, this is run through with a very quick example. You know, if the value you get out is 0.7, you're going to tell a patient that unfortunately their tumor has a 70% chance of being malignant. Something else that he mentions, which I haven't really written down, this is pretty obvious, but it's essentially saying that the probability of y is equal to 0 given x and these parameters plus the probability of y is equal to 1 given x and these parameters is going to add up to 1, which makes sense because you know you only have two options. So if it's not going to be 1, then it's going to be 0, right? And if you want to write this in another way, you can say that the probability of y is equal to 0 given x with a following set of parameters is going to be 1 minus the probability y is equal to 1 given x and some parameters. Next, essentially, we're just saying that with this function, you know, you're not guaranteed a 1 or 0. You'll get something that's either close to 1 or close to 0, but you have to draw a line somewhere. So we're just going to say that the line's being drawn at 0.5. And this helps you form something called a decision boundary, which is to say that, you know, after a certain threshold, you're going to give it one bucket, but before that threshold, you're going to put it in another. And these decision boundaries aren't always linear. So this sort of formalizes the like conversation around the decision boundary. Y is equal to 1 if the hypothesis, if the value output is going to be greater than or equal to 0.5 and 0 otherwise. But these boundaries aren't always going to be linear. So, for example, you could have something like this.
How can I get logistic regression finds the decision
The
boundary?
decision boundary is going to look something like that. And in fact, most of the time, these boundaries won't be linear because your problems are going to be complex. And if you know they were so easy that you could figure it out or draw it, then chances are you don't really need to be using these methods anyways. And this is just another example of a decision boundary that you could have. So something else that we're going to need for our logistic regression to work well is a new cost function. And the reason that we need this new cost function is because if we use the previous cost function and we introduce our h0x, it now looks like this 1 over 1 plus e to the power of negative theta tx, theta transpose x. And it turns out that this is definitely not the nice convex thing that we want. In fact, it looks a bit janky and there's a lot of local minima that our gradient descent could get stuck on. And that will lead us to a non-optimal result. So what we do is we want to basically find a new cost function that is nice and convex and will lead us to a global minima when we apply gradient descent. And he doesn't go through it, but essentially what is commonly accepted as a better logistic regression cost function for the better cost function for logistic regression is this one here. So if y is equal to 1, you're going to set your cost function as negative log hypothesis function x. And if y is equal to 0, it's going to be set to negative log 1 minus hypothesis function x, which we saw previously. Well, we didn't see this part previously. And this sort of makes sense because if you look at the function itself, it's going to set the cost equal to 0 if y is equal to 1, because you know your hypothesis function of x is going to equal to 1. But as your h0 of x goes towards 0, your cost is going to tend towards infinity, which essentially captures that sort of behavior that you want, where you want your model to force a value to 1 if the actual label is equal to 1. And on the flip side, if your label is equal to 0, then you have this cost function here, which is negative log 1 minus h of x. So if your y is actually equal to 0 and you give a value of y is equal to 1, then your cost is going to tend towards infinity. But if it's close to 0 or at 0, then your cost will be much lower or equal to 0. And if we want to put all of this together, then the actual cost function that's normally actually written down is this here. So you get negative y log h of x minus brackets 1 minus 1, 1 minus y log 1 minus h of x. And this works out because you know that y is always going to be equal to 0 and 1. So you're going to have two situations, which he sort of illustrates down here. If y is equal to 1, then your cost function is going to look like negative log h of naught x, and the reason for that is because 1 minus 1 is going to be equal to 0. This term cancels out, and on the flip side, if y is equal to 0, then this term is going to cancel out because you're multiplying by 0. You're going to get negative log 1 minus h of naught x. And this this cost function has a flow-on effect of essentially updating our gradient descent algorithm. But it turns out that after most of what we do, because we're relying on this h naught x, so not h naught x, h of x, it turns out that the base algorithm sort of looks the same. Like for linear regression and logistic regression, your update step will still look like this. The only thing that will be different is that your h of x is going to be this 1 over 1 plus e to the power of negative theta transpose x, as opposed to just the theta transpose x we saw previously. As a brief challenge, Andrew here asked you to do the vectorized implementation of this, which I did down in my notes here. I'll just read it out because writing out mathematics on the computer for me is a huge pain. So I've got j of theta is equal to 1 over m, or negative 1 over m, times essentially negative y transpose times log of h, minus brackets 1 minus y transpose log of 1 minus h. And I basically did that by adapting the previous vectorized version, the previous vectorized cost, which has been presented before. So he then goes on to state, there are other optimization algorithms available, conjugate gradient, BFGS, LBFGS, but realistically, we don't really need to know about them right now. And in reality, we don't really care about these particular optimization algorithms because for neural networks, there are other optimization algorithms that work much, much better. But they have some advantages. No need to pick a manual alpha. Yeah, okay, that's okay. And they're often faster in gradient descent. The disadvantage is that they're more complex, hard to understand, and therefore you might not be able to really fully grasp what it's doing, but you know that it's working, which somewhat ironically is the benefit of machine learning in a way, especially as you get to more complex data modeling. So the next thing that Andrew sort of wanted to cover was this idea of OneVsAll. So normally, when you come to a classification problem, you don't just have one class, you have multiple classes. So this could be the example of, weather, it could be sunny, it could be raining, it could be hailing, it could be snowing. There's these 5 different classes. But the thing is, what we know only works for a situation where you have, one versus the other. So one thing you can do is essentially set up a OneVsAll algorithm where essentially you define a decision, or you're trying to get a decision boundary for the class that you care about, and you say the rest is just junk. We don't really care about that. And that actually works okay, for some situations for simplified logistic regression issues or problems. But if you get to larger ones, it becomes a bit of an issue, and it becomes really tedious to sort of calculate out. When we get to something like machine learning or with neural networks, a more natural solution sort of presents itself in the form of just the basically final output layers. Sorry, maybe not the final output layers, but really just neural networks are poised quite well to deal with this. Not so much they can do linear regression pretty well as well, but normally you wouldn't strictly use a neural network for linear regression. It's a bit of overkill. And to put this OneVsAll slightly more formally, it looks something like this, where you have your h of x is equal to the probability y is equal to I, given a set of values for x and some parameters, where I can be 1, 2, or 3, indicating one of the three classifiers that you've trained. Either the first one where you're looking at triangles versus the rest, or the second one where you're looking at squares versus the rest, or the third one where you're looking at crosses versus the rest. And then towards the end, what you're basically going to do is you're going to, when you want to make a prediction, you just pick the class I that had the highest score. That maximizes this equation here. And the next thing Andrew sort of covered was the idea of overfitting. This is actually a huge problem. This is going to be a problem that you're going to run into almost regardless of how many overfitting techniques you apply. This often comes from a choice of how many parameters you have to what kind of data you have. So what is overfitting? Overfitting is essentially the problem where, for a set of data, instead of learning the underlying trend, your machine learning model has learned that specific data point. So instead of, trying to fit that sort of straight line that you have that we saw with linear regression, it's going to try match that line to every single point. So it's going to look super janky. And obviously it doesn't look correct at all. The underlying trend, it's hard to define, but I think when we look at the data, most of the time we'll be able to tell when something has overfitted. So essentially, once a model has overfitted, the cost is going to go down to very, very close to zero, or zero. And that's a pretty telltale sign that you've done some overfitting. So normally in machine learning, for a straight model, you can't actually, or you really shouldn't be getting a cost of zero or a accuracy of 100. That's a really good sign that you need to stop, pause, and take a look at your model, take a look at your data, and really assess what's happened. So what else have I written here? So, the problem is that I've told you what overfitting is. I haven't told you why it's bad. It's bad because when you don't actually learn the trend of the data, when you don't learn the structure of the data, and you just learn the data itself, it won't generalize to new data. So if you want to actually use your model to make predictions, well, unless you've got data points coming in that are the exact same or very, very, very close to what you've seen previously, then your model is not going to be able to predict anything that's really valuable. And if you did have data like that, well, then there's no point in training a machine learning model. You should just make a hash map or use some sort of fuzzy logic to get close to basically the previous data that you had. Let's see if he has a graph here that sort of explains this in more detail. Yep, it looks like I remembered correctly. So in the case of linear regression, this looks okay. Maybe a bit off with data that looks like, this, then the straight line obviously isn't correct. This looks much, much better. Obviously every single point isn't on the line, but you can tell that the trend of the data has been captured, and there'll be some noise from the way you've measured your data or from whatever else that is affecting the data points as well. But I think quite obviously this one is very overfitted. The graph just looks super off. So here we've got a different example, but now with logistic regression, and you're trying to draw the decision boundary basically for this data set. And you can sort of tell that, the more simple one is quite clearly not right. It hasn't captured the underlying pattern of the data. This one, even though it sort of misses a few cases, it definitely has the pattern better. You'll sort of find out as you go along that with the real world data often isn't as clean as you would hope. So you often get cases where there's misclassifications or gray areas where there really isn't a good way to classify or draw a decision boundary. But if you try too hard and you try to really exclude everything, then you might get a decision boundary that looks something like this, which I think is a pretty clear indication that something has gone wrong, and you should be able to see that, right? So there are a few ways that we can combat overfitting. The first one that, or I guess the two issues that Andrew has sort of identified is that one, you have too many features for the amount of data that you have. And second is regularization, where essentially your model has been a bit too keen to learn to those features. The first one is, I think, quite interesting. This touches on something called the curse of dimensionality, which essentially means that, for a given amount of dimensions, you're going to need more data to actually be able to model those dimensions and be able to figure out what's going on in those dimensions. So if you have, say 10 dimensions or features for your data set, the amount of data points that you might need might be like 20 or 100. But if you had 10,000, then suddenly the amount of data points that you have is much, much greater. And if you don't have those data points to suit, then you're probably going to get some level of overfitting. So one way to combat this is to manually select which features to keep, that is discard features. You can do some dimensionality reduction as well. Something else that happens is sometimes if you immediately go to, say, a linear regression model that is polynomial, it can be too complex for the actual data itself. So normally with these things, you want to start off a bit simpler with something like a linear model, and then you can slowly add non-linear components as you go along. But if you start off with a super complex one, then chances are the model won't know. Well, it will try to use everything it has at its disposal, and what is it trying to do is trying to match the data. So it's going to use everything it has at its disposal to match those data points, and if you give it a lot, then chances are it will succeed in matching the data points almost exactly, which causes overfitting. So let's see what happens with regularization. I think that's coming up next. He's put down here, with regularization, we keep all the features, but we reduce the magnitude or values of parameters theta j. This works well when we have a lot of features, each of which contributes a bit to predicting y. And how this regularization sort of works is that, well, the idea is that a simpler hypothesis is less prone to overfitting. And how do we get a simpler hypothesis? Well, we make it so that each of our x terms don't come into play too much. And what that essentially means is that we want, for each of these x terms, we want the effect to be minimized. So therefore, we want these parameters to be minimized. Here he's written that we want them to be near zero. That's not really the case, but we want them to be low. We don't want them to blow up out of control. So what we do is we add this function here to our cost function, which is to say that essentially if theta is really large, we're going to be basically penalized through what our final cost function is calculated out to be. So the network, or not the network, but the model itself has an incentive to keep these theta values low. He did also point out that we start from theta 1 and go up to theta n, so we won't actually touch theta naught. There's no real given reason, it's just a convention at the time. And if this sort of plays out, it turns out that we get, with these minimized theta values, that we get a curve that looks much more similar to this. So if you saw in the previous one, you would have noticed that sorry, if you saw on the previous slide, you would have noticed that we have this lambda term in front. This is basically something else that we want to optimize. We want to choose lambda such that theta 1, 2, 3, 4, blah 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 can get squished enough, but aren't too squished that essentially they all just go to 0, because if they all go to 0, then what happens is we're only going to have essentially this theta naught. And in the case of the house prices example, you're just going to have a straight line. You're going to say all house prices are the same. I think that's illustrated here. And in this case, you've underfit severely. And what effect does regularization have on gradient descent? Essentially, this is a derivation of the new gradient descent algorithm. So for theta naught, that's not covered because, again, our regularization doesn't cover theta naught, so that stays the same. But for theta of 1 through to n, or theta j in this case, when we add in our regularization term, it looks something like this. And if we do the derivation, if we do the math, essentially, our new update step looks something like this. So the thing to notice here is that this is basically what we had previously, and this is the new thing that we've added, 1 minus alpha times lambda over m, and this 1 minus alpha times lambda over m is essentially what keeps our updates low. So it's going to essentially have a basically like a braking sort of effect on this theta j. So in this case, the example uses is 0.99. So for example, the next theta j is going to be 0.99 theta j minus the update step. So something else that was covered is that this works for the normal equation as well. You can regularize that, but your excuse me, your matrix will look something like this, where the first diagonal is equal to 0 because you're not touching that first parameter, but the rest will be 1s and the rest will be 0s. And this actually has an interesting effect, which is that it makes your it makes those matrices that previously were non-invertible, where m, the number of data points you had, was significantly lower than your features. Sorry, not significantly, was either lower than or equal to your features. It makes those matrices invertible now as well. If you're using MATLAB or Octave, as Andrew was talking about, you could have used pinv, but now you can use inv, which is the inverse, which is pretty much available in almost all matrix libraries for Python, C++, whatever. This, of course, is also going to be applied to logistic regression as well. So regularization, sorry, with logistic regression will look something like this, where cost function was what we had previously, plus we add on the regularization term, regularization term, apologies, of lambda over 2m multiplied by the sum of these parameters squared from j is equal to 1 all the way up to n. And the derivative of this looks something like this. To be honest with you, it's not very different from the linear regression version. The only thing that's really different is this h of x, which we've discussed previously, is going to be equal to 1 over 1 plus e to the negative theta transpose x, that sigmoid function. Cool. So that's it for this week. To be honest, I actually don't know if this is all in one week. I forgot to put down a marker for week 4 in my notes. But for the next week, we're going to be looking at neural networks, which is quite exciting. That's when things really start picking off in the machine learning space. That's not to say that, what we've looked at so far is unimportant. It's one, laid a really good groundwork for our knowledge going forward. And two, a lot of these techniques actually you might revisit even when you have more powerful ones available, because as we sort of touched on with the regularization, sometimes simpler is best. If you can't make something work with a simple model, then chances are that a more complex model will just complicate things.